For over a century, the Panama Canal stood as a pivotal artery in global trade, a testament to early 20th century engineering. Its narrow confines, however, began to restrict the burgeoning scale of modern shipping. As the world's cargo vessels grew exponentially in size, the original canal, once a marvel, became a bottleneck. The vision of a wider, deeper waterway was born not merely from ambition, but from an undeniable economic necessity to sustain Panama's relevance and keep pace with an evolving maritime landscape, ensuring uninterrupted global commerce. The turn of the millennium heralded the Post-Panamax era, a new generation of colossal container ships, bulk carriers, and LNG tankers. These leviathans of the sea, designed for maximum efficiency, simply couldn't fit through the original canal's locks. Their dimensions, wider beams, deeper drafts, and longer hulls, necessitated a radical overhaul of the Panama Canal's infrastructure. Without expansion, these massive vessels would be forced to take longer, more costly routes around the tip of South America, negating the very purpose of the canal and impacting global supply chains profoundly. In 2006, the people of Panama overwhelmingly voted for the audacious third set of locks project. This wasn't just an upgrade, it was an entirely new channel designed to run parallel to the original, equipped with locks capable of handling the largest vessels. The goal was clear: double the canal's capacity and cement its status as an indispensable transit point for another century. This ambitious undertaking, projected to cost $5.25 billion, represented a monumental investment in the future of global maritime trade and Panama's economic sovereignty. At the heart of the expansion lay a groundbreaking engineering innovation, the new Neo-Panamax locks. Unlike the original gravity-fed system, these locks incorporated 3 water-saving basins per chamber. This design was crucial for sustainability and efficiency, especially in a region prone to drought. Each lock complex, located at the Atlantic and Pacific entrances, was conceived as a marvel of modern hydrology and structural integrity, allowing mammoth ships to be lifted and lowered with unprecedented precision and significantly less fresh water consumption. The innovative water-saving basins are a game-changer. For each transit, a ship requires 50 million gallons of fresh water. The new system captures 60% of this water as it drains from the lock chambers into 3-tiered basins. This stored water is then reused for the next vessel, significantly reducing the demand on Gatun Lake, the canal's primary freshwater reservoir. This ingenious closed-loop system mitigates environmental impact and addresses concerns about water scarcity, ensuring the canal's long-term operational viability in a changing climate. The new locks fundamentally changed the types of vessels that could traverse the canal. The original locks were built for ships up to 32.3 meters wide, 294.1 meters long, and with a draft of 12 meters. The Neo-Panamax locks accommodate vessels almost 50% wider and longer, with a significantly deeper draft. This expansion effectively opened the canal to 96% of the world's container fleet, up from just 45% previously. This increased capacity meant a paradigm shift for global shipping routes and logistics, allowing for economies of scale. Building the new locks required an astonishing amount of material. Over 4.5 million cubic meters of concrete were poured, enough to build a stack of Empire State Buildings. This concrete was reinforced with hundreds of thousands of tons of steel rebar, creating structures designed to withstand immense hydrostatic pressures and seismic activity. The sheer scale of material transport and placement in a challenging environment tested the limits of modern construction logistics, turning the canal zone into a colossal, meticulously choreographed industrial ballet. The lock gates themselves are an engineering marvel. Instead of the miter gates used in the original canal, the new locks feature rolling gates, each weighing over 3,000 tons and standing as tall as a 10-story building. These gates operate on giant wheels, retracting into recesses in the lock walls. This design provides superior structural integrity and operational efficiency for the wider chambers. Fabricated in Italy and transported across the Atlantic, their precise installation was a critical and delicate phase of the construction, demanding absolute accuracy. Building in Panama's tropical climate presented a formidable array of challenges. The intense heat and humidity stressed both machinery and human workers, while torrential rainy seasons transformed vast areas into muddy quagmires, disrupting schedules and making ground transport treacherous. Disease vectors, once a major problem during the original canal's construction, were managed through modern health protocols, but the constant battle against the elements remained. Every day was a testament to human resilience and engineering adaptability. Beyond the climate, the geological conditions of the Isthmus of Panama posed significant hurdles. Excavating millions of cubic meters of earth and rock for the new channels and lock foundations required advanced blasting and earth-moving techniques. The region's seismic activity also demanded that all structures be built to rigorous earthquake-resistant standards. Engineers had to contend with varying soil compositions, bedrock inconsistencies, and the sheer volume of material to be removed, transported, and repurposed across the expansive construction zones. The Panama Canal expansion was a truly international undertaking, employing a vast and diverse workforce that peaked at over 30,000 individuals from across the globe. Engineers, construction workers, logisticians, and specialists converged, bringing varied expertise to the project. Coordinating this massive human resource, along with an intricate supply chain of materials and equipment, required sophisticated project management. Daily operations involved thousands of simultaneous tasks, from concrete pouring to heavy equipment operation, all meticulously orchestrated to meet ambitious deadlines. The $5.25 billion price tag for the expansion was a colossal sum. It was primarily funded through a combination of sovereign debt issued by the Panama Canal Authority, ACP, and commercial loans. The financial model was underpinned by projections of increased revenue from higher transit fees for larger vessels and greater traffic volume. This self-financing approach demonstrated confidence in the canal's enduring economic value and its ability to generate significant returns on investment, making it a powerful example of infrastructure funding. The cost-benefit analysis for global shipping was overwhelmingly positive. For carriers, the ability to use Neo-Panamax vessels translated into significant economies of scale. Instead of sending two smaller ships, one larger vessel could transport the same cargo, reducing fuel consumption, crewing costs, and overall operational expenses per unit. Furthermore, avoiding the longer route around Cape Horn saved days or even weeks of transit time, leading to faster delivery, reduced inventory holding costs, and a more responsive supply chain. For Panama itself, the expansion project was an enormous economic catalyst. Beyond the direct revenue generated by transit fees, the construction phase created tens of thousands of jobs and stimulated local industries. Post-completion, the increased canal traffic and larger ships mean higher tolls, contributing directly to the national budget. The canal's sustained competitiveness also reinforces Panama's position as a regional logistics hub, attracting further investment in port infrastructure, warehousing, and ancillary services, driving long-term economic growth. The expansion immediately began redrawing global maritime trade maps. The most significant shift was the rerouting of cargo from Asia to the U.S. East Coast. Before, many Asian goods destined for the eastern U.S. would arrive at West Coast ports, then be transported overland by rail or truck. Now, larger ships can pass directly through Panama to East Coast ports, reducing inland transportation costs and transit times for many goods, making these routes more attractive and cost-effective for shippers worldwide. The transformation didn't stop at the canal. Ports along the U.S. East and Gulf coasts embarked on extensive modernization projects to accommodate the new Neo-Panamax vessels. This included dredging deeper channels, raising bridge clearances, and investing in larger cranes and expanded terminal facilities. Ports like Savannah, Miami, and New York strategically invested billions to become big ship ready, competing fiercely for the increased cargo traffic enabled by the expanded canal. This created a ripple effect of infrastructure development. Beyond its economic imperatives, the expansion also aimed for environmental stewardship. The water-saving basins significantly reduce freshwater consumption from Gatun Lake, a critical ecosystem and source of drinking water for Panamanians. Additionally, the shift to larger ships reduces the carbon footprint per ton of cargo transported, as fewer, more efficient transits are required. Strict environmental impact assessments guided every stage of the project, demonstrating a commitment to balancing progress with ecological responsibility in a sensitive tropical region. Navigating the new, larger locks required advanced safety protocols and new technologies. Specialized tugboats, designed for greater maneuverability and power, were commissioned to guide the Neo-Panamax vessels. Advanced GPS systems and sophisticated training simulators ensured pilots and crews could handle the immense ships with precision within the tighter tolerances of the new chambers. This commitment to safety minimizes the risk of accidents, protects the canal's infrastructure, and ensures the continuous, efficient flow of global commerce. The expanded Panama Canal, often referred to as the third lane, is more than just an engineering marvel, it is a symbol of foresight and resilience. It demonstrates humanity's capacity to adapt and innovate in the face of changing global demands. This monumental achievement ensures that the Panama Canal remains at the forefront of international trade infrastructure, reinforcing its strategic importance for generations to come. It truly redefined what was possible in maritime engineering. The Panama Canal expansion continues to shape the future of maritime trade. As global commerce evolves and ship sizes potentially grow even larger, the canal's adaptability will be key. Its strategic importance as a shortcut between two vast oceans ensures its enduring relevance. The lessons learned in its construction, from innovative water management to overcoming complex tropical challenges, serve as a blueprint for future megaprojects worldwide, proving that with vision and determination, even the most ambitious engineering dreams can become reality.